Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 46. In this video, we prove two theorems. So this video is lengthiest video, takes at least 30 minutes. Let us see the statement of first theorem. The mapping pi maps h into h star defined by pi of y is equals to fy, where fy of x is equals to inner product of x comma y. Then this pi is 1 to 1, onto, additive, but not linear and an isometry. So we prove every property. And remember that the mapping pi that maps from h into h star defined by pi of y is equals to fy. Pi of y is equals to fy, where fy is nothing but inner product. This fy of x is nothing but inner product of x comma y. Inner product of x comma y. So you have to show that this pi is 1 to 1 mapping, onto mapping, additive, but not linear. It is not a linear mapping, and you have to show that it is an isometry. So we show that every property. The first one, to prove that pi is 1 1. Pi is 1 to 1. To prove that pi is 1 to 1, let us take two elements. y1 comma y2 belongs to capital H. Remember that here H is a Hilbert space, H star is conjugate space. Let y1 comma y2 belongs to capital H. Then by definition, pi of y1 is equals to fy1 and pi of y2 is equals to fy2. So to prove that f is 1 1, I mean pi is 1 1, suppose pi of y1 is equals to pi of y2. By definition of this pi, you can write fy1 is equals to fy2. It means fy1 means fy1 of x is equals to fy2 of x for all x belongs to capital H. So this can be written as, by definition, we see the statement here, fy of x is equals to inner product of x comma y. So fy1 of x is equals to inner product of x comma y1 is equals to inner product of x comma y2. So again, this can be written as simply inner product of x comma y1 minus inner product of x comma y2 is equals to 0. Again, it can be written as inner product of x comma y1 minus y2 is equals to 0 for all x belongs to capital H. By taking x is equals to y1 minus y2, remember that we are choosing this one. By taking x is equals to y1 minus y2, you simply get y1 minus y2 comma y1 minus y2 is equals to 0. This condition implies as y1 minus y2 is equals to 0, which implies as y1 is equals to y2. So we prove that, therefore we prove that pi of y1 is equals to pi of y2 implies as y1 is equals to y2. Therefore, we conclude that pi is 1 1. Pi is 1 to 1 mapping. So next we have to show that this pi is onto. This pi is onto. Onto means every element of the codomain has at least one pre-image in the domain. Let us take f is an arbitrary functional in H star. F is an arbitrary functional in H star. H star is the conjugate space. By previous theorem, there exists a unique vector. We learn in the video 45. There exists a unique vector y such that f of x is equals to inner product of x comma y for all y belongs to capital H. Here by our definition, f is equals to fy. Also we have pi of y is equals to fy, which is equals to f. What it means? There for every f belongs to H star. H star is codomain. there exists an element, f that belongs to H domain such that pi of y is equals to f. Pi of y is equals to f. Therefore, we conclude that pi is onto. That is the onto definition. Every element of the codomain has at least one pre-image in the domain. Therefore, pi is onto. Now, we are going to prove pi is additive. To prove that pi is additive. To prove that pi is additive, again let us choose two elements. Y1, y2 belongs to capital H. Then pi of y1 plus y2 is equals to fy1 plus y2. Again, this can be written as fy1 plus y2 means fy1 plus y2 of x. This can be written as inner product of x comma y1 plus y2. Again, it can be written as inner product of x comma y1 plus inner product of x comma y2, which is equals to f y1 of x plus f y2 of x, which is equals to f y1 plus f y2, which is equals to pi of y1 plus pi of y2. So what we prove that pi of y1 plus y2 is equals to pi of y1 plus y2 is equals to pi of y1 plus pi of y2. Therefore, we conclude that pi is additive. Pi is additive mapping. Pi is additive mapping. So already we show that pi is 1, pi is onto, pi is additive. So next we show that pi is not linear. To prove that pi is not linear, it is not a linear mapping. To prove that pi is not a linear mapping, let us take an element y belongs to capital H and alpha is any scalar. Alpha is any scalar. Then pi of alpha y is equals to f alpha y. F alpha y means f alpha y of x. By our statement, this can be written as inner product of x comma alpha y. This can be written as, by the properties of inner product, it can be written as alpha bar into inner product of x comma y. It can be written as alpha bar into fy. Alpha bar into fy of x, or simply alpha bar fy. Alpha bar fy. Therefore, what we show that pi of alpha y is equals to alpha bar into fy. Alpha bar into fy. Therefore, thus the mapping pi is not linear. Not linear. What it means? Linear means pi of alpha y is equals to alpha into pi of y. Alpha into pi of y. This is nothing but fy is nothing but alpha bar into pi of y. So if it satisfies this condition, then it is linear. But pi transforms alpha into alpha bar conjugate. The mapping pi transforms alpha into alpha bar. That's why it is not linear. Whenever it is linear, it transforms alpha into alpha only. So here it is not possible. It transforms alpha as alpha bar. So it is not a linear mapping. It is not a linear mapping. That's it. Right. Next, pi is not a linear. So already we show that pi is 1, pi is onto, pi is additive and pi is not linear mapping. Next, you have to show that pi is an isometry. To prove that pi is an isometry. Right. To prove this pi is an isometry, again choose two elements. Y1 comma y2 belongs to capital H. Now consider norm pi of y1 minus pi of y2, which is equals to norm fy1 minus fy2, which is equals to norm fy1 plus f minus y2, which is equals to norm fy1 minus y2, which is equals to norm y1 minus y2. Therefore, we show that norm pi of y1 minus pi of y2 is equals to norm y1 minus y2. This condition shows us pi is an isometry. Pi is an isometry. This completes the proof, hence proved. We prove every condition. Pi is 1 1, pi is on 2, pi is additive, pi is not linear, and pi is an isometry. That's it. So you check it, one of the derivative part, this is completely derivative part, so easy to prove. And also remember that here this condition pi is not linear, pi is not linear, pi of alpha y, pi of alpha y is equals to alpha bar into pi of y. This is important one. It is useful to prove the next theorem also. So right, let us start our second theorem. So in this video we prove two theorems. This is the first theorem and let us see the second theorem. The statement of second theorem is, if H is a Hilbert space, then H star is also a Hilbert space with respect to the inner product defined by fx, inner product of fx comma fy is equals to inner product of y comma x. So it is also simple theorem, we prove it. I repeat the statement, H is a Hilbert space, H star is also a Hilbert, then H star is also a Hilbert space with respect to this inner product, fx fy is equals to inner product of y comma x. So let us start. Since capital H is a Hilbert space, H is a Hilbert space, then obviously H is a normed linear space. Normed linear space. So it means H star is a Banach space. H star is a Banach space with suitable definition. With suitable definition of addition. With suitable definition of addition and scalar multiplication. Addition and scalar multiplication in H star and norm of the function, norm of a function in H star. This is the important point. It is true without, trivially true without any proof. H is a normal linear space, then obviously H star is a Banach space because it is defined over the complex numbers. With suitable definition of addition and scalar multiplication, everybody knows the addition in Hilbert space and scalar multiplication, H star in H star and norm of the function in H star. Now, in order to prove that, we have to prove that, what is our aim? We have to prove that H star, we have to prove that H star is a Hilbert space. H star is a Hilbert space with respect to the given inner product fx comma fy is equals to inner product of y comma x. Remember the definition, fx comma fy is equals to inner product of y comma x. So to prove this, we have to prove that or we have to show that the following four properties. The following properties. The first one, alpha fx plus beta fy comma fz is equals to comma fz. This is z. Fz is equals to alpha into fx comma fz plus beta into fy comma fz. This is the first property. And the second one is fx comma fy bar, I mean conjugate of inner product of fx comma fy is equals to inner product of fy comma fx. And the third condition is inner product of fx comma fx is equals to norm fx square. Norm fx square. So in order to prove that H star is a Hilbert space, with respect to this inner product of fx comma fy is equals to inner product of y comma x, we have to show that these three conditions. I think if you are aware of inner product space, these are the properties of an inner product space. So anyway, we prove this. We know that by previous theorem, f alpha y is equals to alpha bar into fy. Fy. We learned this condition in the previous theorem. So now we prove one by one. One by one. So this F alpha bar into Fy also can be written as F alpha bar y. F alpha bar y. So we are going to start the first condition. Alpha fx plus beta fy comma fz is equals to, by definition of inner product or by definition of this condition, it can be written as f alpha bar x plus f beta bar y comma fz. So it can be written as simply inner product of f alpha bar x plus beta bar y comma fz. You can split f alpha bar x, f alpha bar y, f beta bar y. It can be written as simply inner product of z comma alpha bar x plus beta bar y. That is the definition here. You see here, inner product of fx comma fy is equals to inner product of y comma x. So by using the definition here, you can write like this. In the statement we have a definition, inner product of fx comma fy is equals to inner product of y comma x. So applying that here, this condition can be written like this, z comma alpha bar x plus beta bar y. So again it can be written as alpha double bar z comma x plus beta double bar z comma y. So again it's simply alpha zx inner product of zx plus beta inner product of zy. This is nothing but alpha inner product of fx comma fz plus beta inner product of fy comma fz. So what we show that, therefore we conclude that here alpha inner product of alpha fx plus beta fy comma fz is equals to alpha into inner product of fx comma fz plus beta into inner product of fy comma fz. That's it. This is the first property. Next we are going to show the second property. So what is the second property? Inner product of fx comma fy is equals to inner product of y comma x. Let us take the conjugate. Inner product of fx comma fy conjugate is equals to inner product of y comma x conjugate. This is nothing but inner product of x comma y. This is nothing but inner fx comma not fx, I'm sorry, this is fy comma fx. Therefore we conclude that inner product of fx fy conjugate of inner product is equals to fy comma fx. So this is the second condition. Now we are going to prove the third condition. Inner product of fx comma fx is equals to inner product of x comma x. This is nothing but norm x square. This is nothing but norm fx square. Therefore we conclude that inner product of fx comma fx is equals to norm fx square. So we prove all the three properties which are required. From this we conclude that h star is also, what is that? H star is also a Hilbert space. H star is also a Hilbert space with respect to the inner product defined by inner product of fx comma fy is equals to inner product of y comma x. This completes the proof of the second theorem also. In the same video, we learn one important note point or important lemma, note point without proof. Let us learn this note point. Suppose we denote the elements of H star. We denote the elements of H star by capital F small f and capital F small g. We denote these are elements, ff and fg are the elements of double conjugate, second conjugate space, where this f comma g are corresponding elements in H star conjugate space. H double star means second conjugate space, H star means conjugate space. The elements capital Fy, capital F and small f, capital F small g are elements in the second conjugate space, where f comma g are corresponding elements in the conjugate space. Then by the previous theorem, this H double star, this H double star is also a Hilbert space, is also a Hilbert space, with respect to the inner product defined by ff comma fg is equals to inner product of g comma f. This is clearly an application of this theorem. So keep learning. Wish you all the best. In the next video, we'll learn the reflexiveness of the Hilbert space.